Bismillahirrahmanirrahim. Assalamu alaikum. Today is our lecture 6 and we are going to study sampling theorem in it. What is sampling theorem? It specifies the minimum rate at which a continuous signal need to be sampled so that the original signal can be recovered. For example, we have a signal and we want to recover it. What should be the criteria according to the sampling theorem? The sampling frequency of that signal must be twice of the maximum frequency of that analog signal, where omega s is the sampling frequency and omega is the maximum frequency of that analog signal which we are trying to recover. Let we have a signal in analog signal to be converted to discrete, and how we can convert a signal from analog to discrete by multiplying it with an impulse train. An impulse train is nothing but a train of spikes at consecutive values, and when we multiply the impulse train with the analog signal we get this kind of sampled signal, and after sampling the values between the spikes are discarded. And how we can recover them? We can extract them back by uh, doing frequency analysis and different analysis that we have already discussed in some of our last previous lectures. mm, Take an example. Here we have a signal. This is actually an impulse signal, and its Fourier transform will be this. The Fourier transform have 8 samples, so its maximum frequency will be, as it have 8 samples, n is equals to 8, so maximum frequency omega m will be 8 by 2 equals to 4. So x of 4 is equals to what? 1 0 1 2 3 4. X of 4 is equals to 1. Its maximum frequency will be 1. Let's check if we shift our impulse signal, what is the effect on its Fourier transform. In this case we have shifted our impulse signal by 1, and in this case our the result will be this. This will be the Fourier transform of this shifted impulse signal. You can see that there is a difference of pi by 4 in all the consecutive values. In the next example, we have shifted our impulse signal by 2 steps, and here the difference between the consecutive values is pi by 2. So from these results we can conclude that if we have a circle, and as here we have 8 samples, so we have divided this circle into 8 parts, and we have shifted our impulse signal by 1, so there is a difference of pi by 4, means 1 portion of this circle. In the second case we have shifted by 2, and there is a difference of pi by 4, means 2 parts of this circle, or the 2 divisions. So by this we can conclude that the number of divisions will be equal to the number of divisions will be equal to the number of shifts induced in the impulse signal. Now come to the convolution. Convolution is very important topic in the course of DSP. What is convolution? Convolution is the mathematical way of combining 2 signals to form a third signal. If we have to combine 2 signals, what will we do? We'll apply convolution on them. And where it is used to map the impulse response of real room on digital audio signals. And in electronic engineering, convolution of one electronic or electrical engineering, the convolution of one signal with other gives output of linear time invariant system, which is a very important term. Here we have an example of a convolution. Here these are the 2 signals given, and we have to convolve them and create or generate an other new signal. On applying the convolution, the formula for the convolution is this: x of n into y of n, which will give us an other signal, which is z of n. Here y of n is again an impulse signal, and what we do in convolution, first of all we we flip our one of our signal. We will in our case we will flip this impulse signal, and on flipping it we'll get it like this. This is y of n, this, and this is x of n, this thing shows that this is at 0. At origin the value is 2, at 1 there's a value of 3, at 2 value is 0, at 3 the value is 2 again, and at -1 the value is 1. This shows that this value is at origin. Here we have written the value of here we have written the signal y of n, x of n, and we have, first of all we have flipped our signal y of n, which is this, and after that we'll start sliding our signal to the right and left until we get zeros on the right and left, consecutive zero values. Here on sliding this on the right side, one will get here, then here in the next steps. By multiplying them, 1 into 1 equals to 1, 1 into 1, 2 into 1 equals to 2, 3 into 1 3, 0 into 1 0, 2 into 1 1, and 0 into 1 0. On the right side and on the left side there will be all the zeros, and 0 into 0 will be equals to 0. So we'll get the convolution, or the third signal, equals to 1 2 3 0 2. Now for example, this was our input signal and our output signal was this. So to get our input signal back, what we'll do, we'll pass our output signal by a low pass filter, and on passing our signals by a low pass through a low pass signal, we'll get again our input signal. But again the condition is what? The sampling theorem. What sampling theorem says that our the sampling frequency must be twice of the maximum frequency. So if our sampling frequency is twice or 2 times of the maximum frequency, then we'll get this function back. But if the condition is not satisfied, then aliasing will happen here. Aliasing means the overlapping of two consecutive signals or two spikes. What we can do to avoid aliasing, we should the frequency of our sampling signal must be twice of the maximum frequency. If we can't do this, then our signal must be band limited. Band limited means after if our signal is band limited, then this will happen, half of our info will be lost and half will be saved. And that's it for today. Thank you so much.